For Form 4 Chapter 3, there's actually only one trial question that came out from Form 4 Chapter 3. So I added one bonus question here in as well to practice together with you all lah. So very simple. They give us two different solutions, 10% sucrose and 30% sucrose. They ask us to identify solvent and solute. Solvent is always our water. Solute is the molecules that dissolve in the water, so that's called a solute. So here solvent is water, sucrose, which is our sugar, dissolve in the water ma. So sucrose. Next, they ask us draw an arrow to show the direction of water molecule movement that will occur. So water will always go from high to low water potential, hypo to hyper. So it's obviously from 10 to 30. So for those still figuring out, 10% sucrose means you have 90% water. And then 30% sucrose means you have 70% water. So your total obviously have to be 100% because you have only water and sucrose. Sucrose 10, water 90. Sucrose 30, water 70. Next, diagram 1.2 shows the condition of a plant cell which has immersed in distilled water for an hour. So distilled water is obviously 100% water. It's all the time hypotonic solution, meaning water go in already. So this is a turgid condition. And the plant cell is taken out of the distilled water and immersed in a concentrated salt solution for another hour. So if I put in concentrated salt solution, this is obviously hyper, a lot of salt, very little water. So the water is going to come out from the cell. And the cell obviously is going to shrink. It's called flaccid. Okay, but they ask us to draw. So first, draw the cell wall first. So cell wall is like this. You can draw two rectangular. So cell must have two layers. And the plasma membrane will pull away from the cell wall. So there are empty spaces here already. So you basically very small already yourself. The nucleus remain. The vacuole will obviously now shrink. So the two main things you have to show when the cell have shrinked, a plant cell has shrink, is the plasma membrane and of course the vacuole. Because vacuole store water, now there's no water inside already. So that's the two main things you have to label. The rest, not really relevant. And then the others state the condition of the cell. The cell obviously becomes flaccid. If they ask us to explain more, very simple, it's because the solution was hypertonic and then the water molecules diffuse out by osmosis. If it's terbalik, means turgid because water diffuse in because it's hypotonic on the outside. Okay? And for my so-called bonus question here, I'll be doing a movement of substances across plasma membrane kind of question. So a very typical kind of chapter 3 question lah. So this one, they showing us a carrier proteins and got two molecules going in and out of the cell. Now, how do I know this is carrier protein, right? Channel protein is like one straight line longgang in between one. Channel, right, is like, see, like this one can move up. Carrier, sorry, can move on. Channel cannot move on. Another is right for carrier, you can see there's like this thing called the binding site. So the first question, they ask, what are the two types of movement for molecules A and B? So A, you can see is going from high to low. Definitely, I know it's a type of passive transport, but remember, you cannot write the answer passive transport because there are three passive transport. You're going to specifically state which passive transport. So passive transport at carrier protein, at proteins in general, there's only one answer. The answer is facilitated diffusion. So how do I know it's facilitated diffusion? Okay, now for passive transport, there are actually three types. You have osmosis, which is for water. You have simple diffusion, which is for like gases and your non-polar lipid soluble molecules. And of course, the one that we just mentioned, facilitated diffusion. Okay, a bit faster. Okay, so for these two, right, they only can occur at your phospholipid bilayer. For facilitated will only occur at protein. So once I see proteins, regardless carrier or channel, high to low, there's only one answer, facilitated. Okay, and then for B, right, you can see it's low to high. It's going against the concentration gradient. So obviously, that will be active transport. So remember, active is like you are going up the mountain. Low to high ma. So low to high, you need energy. Energy is active lor. Understand? And also, now, if let's say they ask us what's the example of molecule A and B, facilitated at carrier protein, there's only one answer: large molecules. Example of large molecules, there are two: glucose and also your amino acid. If it's a facilitated diffusion at your channel protein, so there's only, okay, by the way, channel protein is no active, there's only one possible transport facilitated. No osmosis, no simple as well. As you mentioned, osmosis simple is only at phospholipid bilayer. So if you see high to low going down the concentration gradient at channel protein, it's also facilitated diffusion. However, the molecules, right, are no longer large. They must be ions, charged ions, like let's say sodium, Na plus, and got plus, got minus one, got charged one, ions. Understand? Yes, so here must be large, here must be ions. Large cannot go and pass through here because already say besar ma, big ma. So this thing, since it's very big, it cannot fit into this tiny longgang. It only can fit through here because carrier can move. Now, if you go to molecule B, low to high, in our Form 4 Chapter 3, movement of substance across plasma membrane, there's only one molecule that can go from low to high against concentration gradient. That will be my ions. So example, you can say sodium ions. So only ions can go from high to low and low to high against and following the concentration gradient, only for ions. So if ions want to go from more to less, they must go from channel protein facilitated. If they want to go from low to high against concentration gradient, must be at carrier and active transport. The next question, very simple. They ask, the movement of molecule B across plasma membrane cannot occur without the presence of substance X. What is X? So for active transport, they need what? They need energy. But X is not called energy. X is a type of molecule that provides energy. It's called your ATP, adenosine triphosphate. But ATP is acceptable. Okay, for the next question, they're asking about something called the liposome. So, if you forget what is liposome, liposome is a man-made phospholipid bilayer to mainly contain medication or drugs. Okay, because certain drugs, right, they can be easily destroyed by your stomach acid, the gastric juice. So I want this phospholipid bilayer to protect it because gastric juice cannot break down this phospholipid bilayer. So after my stomach, it will go into the small intestine, whereby small intestine has enzymes like lipase, for example, to break down the phospholipid bilayer. But once it reaches my small intestine can then directly absorb the substance inside. So that's the purpose of a liposome. So for this question, instead of saying drugs, medication, right? Okay, they say that my liposome inside have cells, like living cells, they can help my body. So 4.2 is a graph that shows relationship between use of liposome in the drug R delivery system and the death of normal cells. So they're referring to the cells inside the liposome. You can see without liposome, I have higher percentage of cells dying. With liposome, I have lower percentage of cells dying because they are well protected by the liposome from your gastric juice, obviously. So the question then asks, explain the effect of use of liposome in the drug delivery system. So obviously with liposome, the drug delivery system will be more effective. Because the liposome protects it. So like we mentioned just now, the liposome protects these living cells from being damaged by your gastric juice. It protects healthy normal cells from being damaged by the gastric juice. So that is why it is more effective a bit, because it's being protected. So once you reach your small intestine, then only I break down this phospholipid bilayer to absorb the cells or whatever content that's inside it lah. So questions quite commonly to ask about, let's say, supplement like vitamin C. So if they ask how liposome can help vitamin C to be more effectively absorbed by your body, same. It has a phospholipid bilayer which protects your vitamin C from being damaged, destroyed by your gastric juice. Same answer. The next question, they ask another use of liposome. So other than carrying drugs, medicines, what is it used for? Now, in our textbook, there's this example. They say that it's used for cosmetic, like facial cream, for example. So you can say it's for cosmetic products, like facial cream, like that. So same, this thing also can, because some facial products, they have active ingredients, we have living cells inside it. So this liposome is to protect it. So once I want to use it, I just like squeeze this liposome so it will burst and the cream come out, and I put my face on. then I can the whatever things ingredients is inside can straight away function. So they say here ensures that the active ingredient in the product can reach the skin layer. For liposome, okay, this one seldom will ask, more will ask about the drug. So chapter 3 for this year, Form 4 chapter 3 is not a very common topic. But even if you come out, it's a very simple topic. So yeah, I just do like a few revision for this chapter. So we will continue again. See you in my next video very soon. Bye bye guys.